In this video, we are going to talk about inference for categorical data and the difference of two proportions. And actually, many of the things are totally analogous to our last video where we looked at one proportion. So the idea is we have two populations and we're going to calculate the same proportion for the two populations. So we have a P1 hat and a P2 hat. And we're looking at the difference between them. So P1 hat minus P2. So we want to know, are they different or are they the same? The conditions for a sampling distribution of P1 hat minus P2 hat to be normal is independence, much like for one proportion, but it's extended, and extended because now we have two populations. So the data are independent within and between the groups, so between the two groups. So you analyze population 1 and you analyze population 2, and then together. Generally, this is satisfied if the data comes from two independent random samples or if the data comes from two randomized experiments. The next condition is the success-failure condition, and it must hold for both groups, where we check success and failures for each group separately. When these two conditions are met, then we have this formula for standard error, very similar to the standard error for one proportion, but now we have P1 times 1 minus P1 over N1 plus P2 times 1 minus P2 over N2, all square rooted. From there, because we know our distribution is normal, we can do confidence interval for the difference of two proportions using our standard error. Remember, for confidence interval, we don't know the population parameters P1 and P2, so we use P1 hat and P2 hat as an estimate. For hypothesis testing, we use the null hypothesis that the proportions are equal, that they are not different. And then we have the pooled proportions for the standard error. So P pooled is equal to the number of successes divided by number of cases. And if it's not given to you in a chart where you can easily read off the number of successes and number of cases, you can use this formula here, P1 hat times N1 plus P2 hat times N2 all over N1 times N2. We will do this example here to illustrate all three, the conditions for sampling distribution, confidence interval, and hypothesis testing. And we'll do this example in the main part of our video. So that concludes our summary. And we can now come back and take a closer look at conditions for a sampling distribution P1 hat minus P2 hat to be normal. And again, the two conditions we want to satisfy are independence extended. Again, independence is the same thing we had for proportions. Mainly, we want something with random samples or some data to come from a random experiments. And extended because now that we have two proportions, basically each proportion needs to have been independent. Also, between the two groups should be independent as well. Next, we have the success-failure condition. It's pretty much the same thing we had in our previous video. We'll be doing an example of that in this video. So let's look. So our example is we're going to consider an experiment for patients who underwent CPR for a heart attack and admitted to a hospital. These patients were randomly divided into a treatment group where they received a blood thinner or a control group where they did not receive a blood thinner. The outcome variable of interest was whether the patient survived for at least 24 hours. The results are shown below. Check whether we can model the difference in the sample proportion using the normal distribution. So here are the results. We have the control group that did not receive the blood thinner and the treatment group that did receive the blood thinner. These are the number of people who survived, the people who died, and the totals for each of the control group, treatment group, totals for survived and died. The first thing we want to do then is to figure out our P1 hat and our P2 hat. So our P1 hat will represent the control group. If you want, you could have called that P2, but I used P1 for the control group. So 11 people out of the control group, a total of 50 people, survived. So 11 out of 50, their survival rate was about 22%. For P2, that's the treatment group, 14 people out of 40 people survived. So that's about 35%. So we want to know if this treatment, if this 35 was significantly different from this 22? Is this just due to the random sampling error, or is this a significance difference that says the treatment is what caused the improvement? And before we start using the normal table to do confidence intervals or hypothesis testing, we need to verify that the sampling distribution is indeed normal. The first condition is independence, and because the patients were randomly assigned into treatment and control group, that's a randomized experiment, we can say that independence has been satisfied. The second condition is a success-fail. The success-failure conditions are that we have at least 10 successes and 10 failures. In this case, you can see in the control group, we have at least 10 successes and 10 failures. In the treatment, we also have 10 successes and 10 failures. Your data isn't always given to you this way, so you should also be used to using this formula. For our successes over here, we can look at our control group and say that we have a 22% success rate out of 50 total control group. So 22% times 50, that's 11 successes, which is greater than 10. For the treatment group, we have a 35% success rate out of a total of, this should be 40, sorry, 40 people here. Let me change that. 40 total people in the treatment group. And that's also greater than 10. It's 14, actually. Here is our failure rates. So for our control, where we have 50 people, our failure rate is 1 minus the success rate, 1 minus 0.22, and that's equal to 39, which is greater than 10. And our failure rate for the treatment group is 1 minus 35 times our total number of people, which again, this should have been 40, also greater than 10. So we have verified our two conditions, independence and success fail, so we can assume a normal distribution. Now that we know we have a normal sampling distribution, we can go on to a confidence interval. We're going to use this same example of these heart attack patients. People in the treatment group get a blood thinner, people in the control group do not. We're comparing the survival rates. Survival rates in the control group is about 22%. Survival in the treatment group is 35%. So we want to create and interpret a 95% confidence interval for the difference in survival rate. So first we need to calculate the difference in survival rate, which is P2 minus P1. You could do it the other way around, but I kind of like to work with positive numbers. So I did P2 minus P1, which is 35 minus 22%, which is equal to 13%, or 0.13. For a 95% confidence interval, so around the mean, I want all the data that's 90%, which means above our z-score and below our z-score, we must have 5% in each, right? Because the total area under the curve is 100%, so 100% minus 90% is 10%, and then we divide it up in the two areas here. So for a 90% interval, I'm looking for a z-star such that 95% of the data is below our z-star. So I'm looking for this z-star here so that I can get 95% of the data. And again, the reason why we couldn't just do the 90 is because we want everything below, which matches this picture in our table. So we want everything below. We need to add the 90 plus the 5%. Looking here for 95%, I see we have 0.9495 and we have 0.9505. So it's right in between here. It's between our z-score of 1.645. And I'm going to use the z-score, my 1.6, and I'm just going to go with the 5 at the end. So I'm going to say z-star is 1.65. Next, I want to calculate my standard error, and I have my formula for standard error up here. So let me use that. Standard error is equal to my 0.22 times 1 minus 0.22 over n1, which is 50. My p P2, which is 0.35, and 1 minus P2, which is 1 minus 0.35, over N2, which is 40. So I get a standard error of 0.095. Now my confidence interval is built around my P2 hat minus P1 hat, which is 13%, plus or minus 1.65 times our standard error. So it's our 13% plus or minus, and then I multiply my standard error times my z-score, which is 15.7%. So my confidence interval is negative 2.7% up to 28.7%. And last, I want to interpret what this confidence interval means. It says we are 90% confident. The difference in survival rate is between negative 2.7%. The negative means that sometimes the, the P1 is greater than P2. So sometimes the control group will have a higher survival rate. Again, negative because P1 is greater than P2, and 28.7%. That's when P2 is greater than P1. Because 0% is in the confidence interval. In other words, somewhere in here, it's possible that there's zero difference between treatment and control group. We do not have evidence that the blood thinners have an impact. Or said another way, we are 90% confident that the difference in survival rates is about zero. There's no difference between the blood thinners and no blood thinners. Our next example is about a 5-year experiment conducted to evaluate the effectiveness of fish oil on reducing cardiovascular events. Each subject was randomized into one of 2 treatment groups. We will consider heart attack outcomes in these patients. So people with fish oil, they had 145 people had a heart attack, which seems like a lot, but we look at this, 12,788 had no heart attack. So this is a large number, but only because the total number of people is even larger, 12,933. For the people who received a placebo instead of the fish oil, 200 had a heart attack. That's 12,738 people with no event, for a total of people in the placebo group as 12,938. So we can calculate our P1 and P2, and actually this is it's a sample, so I should have P1 and P2 hat. So the fish oil people, and here we're going to say success, and success at this point we're going to have a little quotes around it, are the heart attack people is 145 over 12,933. So that's approximately 1.12%. For the placebo, the heart attack people, that's 200 over 12,738, which is 1.55%. So we want to interpret a 95 confidence interval for the difference in survival rates. Here I have calculated the difference, P1 minus P2, that's my 1.12% minus my 1.55%, which gives us a negative, because P2 is greater than P1, 0.43%. The first thing I need to do is verify that my probability distribution is nearly normal. The 2 things we need to look at are independence, but these are independent because the groups are randomized here. So subjects are randomized into one of the 2 groups. And second, we can see the success failure rate. We can see each group for the heart attack, fish oil, and heart attack placebo, as well as fish oil no event and placebo no event. They all have greater than 10 successes and failures, so we're good. Next, I calculate my standard error using this formula here. And again, for P1 and P2, for the confidence interval, we're going to use our sample proportions. So I have P1, which is my 1.12, which I converted to a decimal, 0.0112, times 1 minus 0.0112, which is 0.998, divided by N1, which is our 12,933, plus our P2 times 1 minus P2, so P2 again converted to a decimal, 0.0155. 1 minus that is 0.9845 divided by n2, which is 12,938. Taking all of that square rooting, and I get 0.00145. Now, if I want a confidence interval centered around the mean, and I want 95% of that data in the center, that means I have 100 minus 95, 5% on the two ends, which means the top end gets 2.5%, the bottom end gets 2.5%. My table, though, shows z-scores all the area below, so I need to add the 95 to 2.5, which gives us 97.5. So I'm looking here for something with 97.5% of the area, which is somewhere, oh, here it is, 97.5. So 1.96, which means the z-score associated with the 97.5%, that the area is less than z star, is going to be z star equals 1.96. So now I can compute my confidence interval, which is my p1 hat minus p2 hat plus or minus 1.96 times standard error, which I computed here. So I have my difference between the two is negative 0.43% plus or minus 1.96 times my 0.145% will give me a confidence interval of negative 7.1% and negative 0.146%. And again, the negative indicates that P2 is greater than P1. In other words, our P2, our placebo group, had a greater number of heart attacks than our P1, our fish oil group. Finally, you can see that 0 is not in this confidence interval. So in other words, there is a difference, and a consistent difference, that P2 is greater than P1. So P2 has more heart attacks than P1. So we are 95% confidence that fish oil decreases the heart attacks between 0.71% and 0.146%. Next, we'll do some hypothesis testing. Now, in our hypothesis testing, we're trying to see if there's a real difference between the two proportions. So our null hypothesis is going to assume that the proportions are equal. That is, P1 minus P2 equals 0. We're going to use this P pooled proportion, P hat pooled, to estimate P. And we're going to use this to verify the success-failure condition and also estimate the standard error. So this is our P pooled formula. That's the number of successes over the number of cases. By formula, that's going to be P1 hat times N1 plus P2 hat times N2 divided by N1 plus N2. And our standard error formula is going to be equal to the square root of P1, 1 minus P1 over N1 plus P2, 1 minus P2 over N2. And remember, for hypothesis testing, our population proportion is going to be estimated using P naught from our null hypothesis because we're assuming the null hypothesis is true. Our example is a study with 90,000 female participants where each woman was randomized into one of two groups. The first received regular mammograms to screen for breast cancer, and the second received regular non-mammogram breast cancer exams. No intervention was made during the following 25 years of the study, and we will consider the death rates resulting from the breast cancer over the full 30-year period. So here's our chart. We have the mammogram group. There were 500 deaths and 44,425 non-deaths after 25 years. And then we had the control group. And again, this is deaths from breast cancer, not just any death. So in the control group, we had 505 people, and deaths from breast cancer was 44,405 in the 25-year study. And the first question, is the study observational or experimental? And it's experimental because people were randomized into one of two groups. Can we assume a normal distribution? We're going to check for two things. The first is independence, and we will say yes because this is one where the treatment and control group are assigned randomly. So it's independent. And the second thing we need to look at is success failure. And now we need a p-pooled variable for our success failure. So p-pooled is equal to p1 hat times n1. So that's going to be P1 hat times N1. So we actually haven't calculated P1 hat. And the reason is, remember this P1 hat times N1 is just equal to the number of successes for the first group. So that's 500 plus P2 hat N2, that's the number of successes in the second group. So that's 505 divided by N1 plus N2. So N1 is the 500 plus 44,425, and N2 is the 505 plus the 44,405. So our P hat pooled is going to be equal to 0.0112 or 1.12%. Now we can look at the mammogram section. The successes is equal to N times P. So we have the total number times our P now. We're going to use this P hat 1.12, which is 503, so it's greater than 10. Our failures, again, we have so many so many people in this, times 0.98, it's going to be greater than 10. Now looking at our control group, our successes in the control group, we definitely have over 10, and our failures, we definitely have over 10. Our conditions for normal distribution, independence, success, failure, they're both met, so we can assume that the P hats follow a normal sampling distribution. Moving on to our hypothesis test, we need to define our null and alternative hypothesis. So our null hypothesis is that there's going to be no difference. Remember, before we start introducing new kind of treatments, we want to be skeptical. So we generally assume that any new treatment isn't going to produce any better effects than our current techniques. So we always assume P1 minus P2 is equal to 0. No difference between the treatment and control group. For our samples, we found that P1 hat mammogram died is equal to 500 over the 44,425, our percentage of people who died. Remember, we want to make sure, you could have chosen survived, but I did died for whatever reason. So I have 1.125%. Let's contrast that to P2. That's the control group of people who died, and that's 1.137%. So the difference between 1.125 and 1.137 is negative 0.012%. Now, is this a real difference because P1 is so much bigger than P2? In other words, the people who had the mammogram died more frequently than the controlled group? Or is this due to just random sampling error? That's what our hypothesis test wants to determine. To calculate standard error, I'm going to use my regular formula for standard error for difference between two populations, but I need to also calculate this P hat pooled, since now that's what we're going to use for our P. So P hat pooled is equal to, over here, number of successes, that's 500 plus 505, over number of cases, that's 44,000 plus the 500, the 44,405 plus the 505, and that gives us 1.12%. Remember, this is P hat pooled, and now we can calculate our standard error is going to be our P hat pooled, and I converted this to a decimal, 0.0112 times 1 minus 0.0112, and then our 0.0112, 1 minus 0.00112, and both over N1 and N2, and that gives us 0.07%. So what we have so far is our P1 hat minus P2 hat, which is equal to negative 0.012%, is negative 0.17 standard errors from the mean of 0. This is assuming, again, our null hypothesis is true. So we're assuming that our P naught, our null hypothesis, is our mean is equal to 0. Our sample, we have P1 hat minus P2 hat equals negative 0.012, and that's a z-score of negative 0.17. So over here, a z-score of negative 0.17, that represents what we found when we did our sample. And now, essentially, we want to know if our null hypothesis is true, what's the probability of producing a sample with a z-score of negative 0.17? So I'm going to look up the z-score of 0.17. So here's 0.1, here's 0.7. But what we have to remember, this is a negative z-score, and what I've just looked up is a positive z-score. So let me draw this picture for you here. At positive 0.17, we have 56.75, according to this table, underneath z equals 0.17. That means on above z equals 0.17, because the total area under the curve is 100%, is 100% minus 56.75, which means we're left with 43.25% above the z-score of 0.17. Now, this curve is symmetric. That means the amount of area below z equals negative 0.17 must also be 43.25, right? Because now we're using symmetry over here. If this is z equals negative 0.17 by symmetry, this is also equal to 43.25. So I've written this down here. So the area below 0.017 from our table is 56.75. So the area above z equals 0.17 is 100 minus 56.75, which is 43.25. Remember, because the total area has to be 100, it's a probability curve. So that means by symmetry, the area below negative 0.17, that should have been a 7, is also equal to 43.25%. Okay, so that's this 43.25. Since we're trying to determine whether or not P1 minus P2 is equal to 0, these two areas here represent when P1 minus P2 is not equal to 0. In other words, we need to take the case where P1 is greater than P2 or P2 is greater than P1. So we're looking at P1 minus P2 is greater than 0 or P1 minus P2 is less than 0. So we take both tails. So that's 2 times 43.25 is 86.5%. Our p-value then is 0.865, which is greater than the 0.05 that we often use as our level of rejection. This problem didn't give you an alpha value, so we're just going to assume 0.05. So we do not reject H0. In other words, the mammogram is not significantly different from other screening because 86.5% of the time we're going to expect something greater than z equals 0.17 or less than negative 0.17. To review what we've covered in this video, we've looked at difference of two proportions. The idea is we have two populations and we're measuring the same proportion, but for the two different groups. So we have a P1 hat minus P2 hat. We're trying to determine if this difference is greater than or equal to or less than 0. The conditions that the sampling distribution of P1 hat minus P2 hat to be normal is one, independence. So it's our regular idea of independence. Things are independent if they come from random samples or if the data comes from a randomized experiment. And we extend that because now the independence has to be within and between the two groups. And for the random samples, it's just 2 independent random samples or 2 independent randomized experiments. We have the success-failure condition, where we check the successes and failures of each group. When these conditions are met, then we have this formula for the standard error, which is equal to the square root of P1 minus 1 minus P1 over N1 plus P2 times 1 minus P2 over N2, where P1 and P2 represent population proportions and N1 and N2 represent sample sizes. From there, we can do a confidence interval, and we can also do hypothesis testing. For hypothesis testing, for our, like when we need to plug in a p for, say, standard error, we use both p's equal to this p hat pool, and it's based on the number of successes for the first population and the second population divided by number of cases. Otherwise, both the techniques for confidence interval and hypothesis testing are very similar to what we had done in the previous video. So that's it for this video. Thank you for watching.